All right, guys, welcome to the webinar, and this is going to be for the forces test. As always, there will be 20 multiple choice questions. Out of those 20, there will be 18 with one answer choice, and there will be 2 with 2 answer choices. You will have an FRQ section, and there will be 2 of those questions. Of course, there will be multiple parts, but it's pretty much the same format that we've had all year long, and we do keep this format throughout the year. So, forces. What is a force? A force is anything that can cause an object to accelerate. So force is equal to mass times acceleration. What we need to remember is that if there is a net force on an object, then that object has to accelerate. If the net force, or the sum of the forces on the objects, equals 0, then what that means is that the object could be at rest, or it could just be moving at a constant velocity. And the video that we watched in class of the rocket that was sent to Mars, it had some thrusters that gave it a force, and it propelled it through space. But once it was in space and it was trucking along, there was no more thrust force needed. It just continued in motion with constant velocity motion because there were no forces to slow it down. In fact, everything would keep in motion if there weren't frictional forces or air resistance forces to slow them down. Just like if I'm going to slide down this hill on a sled. Let's say this is a snow hill. I slide down the snow hill on the sled. I slide down, and what do? I keep going. I keep going due to inertia. And really, inertia is just a measure of mass, because the more mass I have, the more inertia I have. Inertia is the resistance to change motion. An object at rest tends to stay at rest. An object in motion tends to stay in motion unless acted upon by an outside force. But what happens here is that eventually this block or this sled slows down, and that's because there's a frictional force in the opposite direction that will slow it down. If that frictional force was not there, then that object would just keep moving all along. Of course, we also have the weight force, or the gravitational force. This is the frictional force. And then, of course, the normal force. So let's talk about those two forces really quickly. The weight force, of course, is how much something weighs. And we can use a scale or a spring scale to determine that weight force. But what we need to remember is that weight force is also equal to the force of gravity. These two things are the same thing. A lot of people sometimes use the term force of gravity, not realizing that it is the weight. So how do I find the weight, or find the gravitational force on an object? I take the mass of that object and I multiply it by little g, which is an acceleration. So what we need to remember here is that this gravity is a force, and this gravity is an acceleration. This acceleration is constant, and it is 9.8 meters per second, or in our questions, we typically use 10 to give us a nice, easy mental math to work with. This force of gravity over here is not constant for all objects on the Earth. This value changes for every object because every object is going to have a different weight. Okay, they have a different mass. If two objects have different masses, then they have to have different gravitational forces, and of course they have different weights. So I just want to make sure we all remember and realize that there is a difference between mass and weight. Weight is simply the mass times 10, which is the acceleration due to gravity. So make sure whenever you're talking about gravity that you specify force of gravity or acceleration due to gravity. Those are two very different things. Now, a lot of times the force of gravity is equal and opposite to this normal force. The normal force by definition is a force that is perpendicular to to something. And in this case, it's going to be the surface. So the normal force will always be perpendicular to the surface. So if I have two surfaces touching, there will be a normal force there. And this force is going to go straight up perpendicular to that surface. Now we draw the force coming from the center of mass of that object. But if I were to redraw this, and here's the actual box, the actual force starts at the surface and pushes up, right? But whenever we do a free body diagram, we start the forces at the center of mass because that's effectively where they're all acting upon on that center of mass. The weight force and the normal force are not an action-reaction pair. So Newton's third law says that, typically it says, for every action there's an equal and opposite reaction. But we redefine Newton's third law as if object 1 applies a force to object 2, then object 2 applies an equal and opposite force to object 1. And in this case, the weight force and the normal force, they're never going to be an action-reaction pair according to Newton's third law. And to test whether it's an action-reaction pair, you have to ask yourself how many objects are in the scenario. There should only be 2 objects if I'm talking about an action-reaction pair. When it comes to weight force and normal force, well, what causes the weight force? The Earth does. The Earth causes the weight force because that is the gravitational force, as I already said here, that the Earth pulls on that box. So we have the Earth in this situation, of course we have the box in this situation, and then the normal force is provided by the surface or the ground. And you might be saying, well, isn't that the Earth? Isn't the Earth the ground? Well, the surface isn't always going to be the Earth, but what I'm talking about here is a contact force, and this is a field force. I don't have to be on Earth's surface for that gravitational force to take effect on me. I mean, if I jump off the roof of my house, I'm going to fall down to the Earth. So that weight force or that gravitational force is a field force, whereas the normal force is a surface contact force. So I have the surface, I have the box, I have the Earth. There's 3 objects there. These guys are not action-reaction pairs. And I point that out because they will not always be the same. Those action-reaction pairs will not always, the weight force and the normal force will not always be the same magnitude. When are they the same? If I'm on a level surface, so F of W, which is Fg, or mg, will equal Fn if I'm on a level surface and that surface is not accelerating, like in an elevator. And there are no additional forces acting on that box. Because if I applied an upward force to this box right now, then that would reduce the normal force. The surface wouldn't have to push up quite as much if I applied an upward applied force. So only when it's a level surface and the surface is not accelerating and there are no additional forces, that is the only time that the normal force will equal the weight force. So any other situation, the normal force and weight force are not going to be the same. Okay, let's do a quick summation of forces here for an object that is on a surface, and we'll say that this force here is going to be the weight force or the mg force. This force is going to be the normal force, but I'm going to apply an additional force to this box. So I'm going to have an applied force to that box. The first step to any physics problem is to draw a free body diagram. The free body diagram I've already drawn here. I have a normal force pushing up, I have the weight force pushing down or pulling down, and then I have an applied force. Now, when I sum up the forces, I use Newton's second law. The sum of the forces equals mass times the acceleration of that object. the sum of the forces on that object. I simply look at my arrows and I add up the ones that are in the same direction and I subtract the ones that are in the opposite direction. So the summation equation, which is on the left side here, would look like this. The applied force plus the normal force minus that weight force, which is mg, would equal the mass times the acceleration of this system, or this box. But in this situation, the box is at rest on the surface, so that acceleration is actually 0. So this whole right side of the equation will equal 0. I know we start a lot of problems with sum of F equals ma. On the left side of that equation is where you're going to look at your free body diagram to sum up those forces for you and to write your, so this right here would be your summation equation. Actually, the whole thing is your summation equation. And on the right side here, this is where I ask myself, what is the motion? Is it at rest? If so, then that right side is going to equal 0. Is it at constant velocity? If so, then that right side is going to equal 0. If the object is accelerating or changing its velocity, speeding up or slowing down, then that side will equal ma. Okay? So that's just a basic free body diagram, a basic summation equation. Where it gets a little more complicated is whenever we, maybe the object itself is accelerating. So now let's say this box is suspended by a cable and we have an elevator and we have a person standing in that elevator. And that person, we're going to say, is standing on a scale. And now remember, that scale is not really getting our weight, it's really just measuring our normal force. Scales are really just normal force indicators. Because we all know that if I get on my bathroom scale, I can make the scale read higher or lower than my actual weight simply by pushing up or pushing down on the counter next to me, right? So the scale is really just reading my normal force because I can fluctuate that normal force. So let's pretend we're in an elevator here and the elevator starts out as at rest. When the elevator's at rest, the forces acting on me are going to be equal and opposite. So I'm going to have a weight force here, which is mg, and I'll have a normal force, and that normal force will be the exact same magnitude as the weight force. How do I know that? Because it's at rest, the sum of the forces will equal 0, and the free body diagram says that the sum of the forces is the normal force minus the weight force. Therefore, the normal force is equal to the weight force, or simply mg. So if I know the mass, I can simply multiply that by little g to figure out the mass, or sorry, the weight force, which is equal to the normal force. But now let's say that this elevator starts to accelerate upwards. So we're going to have an upwards positive acceleration. Well, Newton's second law also tells us that if there's an acceleration, then there has to be a net force. There has to be an unbalanced force causing the object to accelerate. And what it also tells us is that the net force must always be in the same direction as the acceleration. So if the acceleration is up, then the net force is also up. And since the net force is up in this situation, I know that for this scenario, the normal force must be greater than the weight force. So I'll redraw that over here. The normal force must be greater than the weight force, which is that mg. So when I write the summation equation for this, it is accelerating, so I'm going to leave that as ma. To figure out the summation of the forces, I look at my free body diagram. I subtract vectors that are in opposite directions. So we're going to have the normal force minus the weight force equal to the ma. And the normal force then becomes, if I add mg to both sides, it becomes ma plus mg. So the normal force is really just the mass times the acceleration plus the gravity. And that makes sense because the tension in this cable here, as it's going up, is going to be greater than if it were falling down. And think about it this way. If the elevator must push me upwards, it first has to overcome gravity and then give me that additional acceleration. So it's going to be g plus a. However, in the reverse situation, if that elevator begins to slow down, because if I speed up and then I can go to a constant velocity, then I can slow down to come back to rest. So if I start at rest in the elevator and I accelerate positively upwards, then I'm going to move upwards. And then if my acceleration, let's say, goes back to 0, so let me draw an acceleration time graph here. So let's say my acceleration starts out at 0, and then it increases to some constant amount, and then it decreases. I need to erase that, don't I? Let's see. If my acceleration increases, and then it goes back down to 0, well, when it's at a 0 acceleration, if it hasn't slowed down yet, then that means that at this point it's at a constant velocity. Then it has to slow down in order to come back to a rest. And this graph is the exact same graph that you guys had on your first test, right? At the beginning, the elevator was at rest. And at this point, the elevator was increasing its velocity, so it had a positive acceleration. Here it was at constant velocity, not at rest, and here it had a constant negative acceleration, and this positive acceleration canceled out that negative acceleration, and so at the end here it was at rest again. Alyssa says on the test, will we have to read, interpret, make graphs like in the past 2 units? Yes, you will have to be able to read and interpret graphs or draw graphs. So in this scenario with the elevator, what I've drawn here at the beginning, well, actually in the blue, this is when it was at rest, and then this is when we had a positive acceleration and it was moving upwards. And then this last case down here, as the elevator gets to the next floor, it's got to slow down before it comes to a stop. So when that elevator slows down, we'll get a third free body diagram. I'll do that one in green. So the third free body diagram will be down here for this green section. And in that case, if it's slowing down, then in the positive direction, the direction of the acceleration is going to be down. So if the direction of the acceleration is down, then the direction of the net force must be down as well. So that means that the weight force, which by the way is the same length for all 3 of these, the mg force should be the same length for all 3 of these because the weight force never changes. What changes is the normal force. And so since the net force must be downward, then I know that that normal force pushing up on me is actually less. So it's kind of like gravity wins. The floor doesn't push up as much, and gravity is actually is winning, and the acceleration is in the downward direction. Now, if the acceleration is in the down direction, does that mean that the motion has to be down? Does that mean that my displacement has to be downward when I'm on the elevator? And that answer is no. And that has to do with inertia. So if I were to draw the velocity time graph for this situation, what we would see is that, let's see, we're at rest at the beginning. So the initial velocity would be 0. Here I have a constant positive acceleration, so I'm going to increase my velocity at a constant rate. Here I am at a constant velocity, therefore velocity is staying the same. So I am moving, and I'm still moving upwards, just with a constant velocity. And then down here, I slow down, I have that negative acceleration, and so that velocity decreases back down to 0. Now, remember that the area under the velocity time graph equals the displacement. And so did I have a net positive displacement or negative displacement? Well, it was positive. So what direction did I move? What direction did the elevator move? I moved up. If my velocity time graph had been down here, then I would have had a negative displacement. And if I had had a portion up top and a portion below the 0 axis, well, then those velocities would cancel out, and maybe I went up and came back down. But in this scenario, I'm moving up the entire time. So just because the acceleration vector is this way does not mean that I'm moving down. I'm still moving up, and here I was at rest, so I wasn't moving at all. I'm moving up, and the acceleration vector is in the opposite direction, so this just means I'm slowing down. And when I'm slowing down in the upward direction, that means that the weight force is greater than the normal force. All right, Tyler Harris, can you do number 1 and 12 on the practice test on the multiple choice? You bet. All right, let's do number 1. Number 1 on the practice test. So I have a wall here, a ceiling, and some cables. And then I have a mast that's hanging from that cable, and they tell me this theta equals 30 degrees. So this system is at rest. So I know that the sum of the forces has to be equal to 0. There is no acceleration, so the sum of all those forces has to be equal to 0. So what is on this side? Well, we use our free body diagram to figure out what the summation of those forces are. So let's look at the center of mass of this mass right here. So that mass right there, I have an upward, let's see, sorry, I have a downward. Is it 50 degrees? Yes, it is 50 degrees, sorry. This is 50 degrees, not 30 degrees. Okay, and what we effectively have in the way of tension forces is we effectively have a portion of our tension force here and a portion of our tension force here. And what I can see when I break everything down into y and x components is that I have a y component to this force, so I would call this Fty, and I have an x component to that force, and I would call this Ftx. And now when I sum up the forces, I have to look at the sum of the forces in the x, which equals 0, and the sum of the forces in the y, which equals 0. The sum of the forces in the x is just this. We'll call this Ft1 and this Ft2. So the sum of the forces in the x is simply this Ft2 force here is equal to the x component of the FT1 force. And so what that means for my vertical forces is that the vertical component of FT1 has to equal this downward, I didn't write mg there, has to equal that downward weight force, which is mg. So the y component of this angle, or this force right here, is what's equal to the weight force. Now I can use trig to figure out what the y component is equal to. If this is my angle, this is my hypotenuse, this is going to be my tension force. This side is opposite of the angle, so I'm going to use sine theta. So FT1 sine theta is equal to mg. Therefore, the tension force is going to be mg divided by sine theta. The mass is equal to 5, g is equal to 10 or 9.8, and sine of 50 degrees goes there. And when we do all of that math, we see that the answer is 64 newtons. So in this problem, it was realizing that the sum of the forces equals 0 because the system's at rest, and also breaking down this component, or sorry, this tension force into its y and x components, and realizing that the y component was the one equal to the downward weight force. All right, he says number 12. Let's look at number 12. Yeah, my answer key for number 12, I wrote it, I guess it was my dyslexia coming out. I was writing, I kind of wrote that one backwards. The answer there is correct, but I was thinking of it in a negative way rather than a positive way. Actually, that was number 13. Number 12, which of the following diagrams best represents the gravitational force of W, the frictional force F, and the normal force N acting on the block? So this is an inclined plane problem. This is wonderful to go over. You definitely need to understand inclined planes. So when I draw the inclined plane here, what we need to remember is that the weight force, the gravitational force, will always go straight down. Okay, so there's my mg. It's going to go straight down, and that is the weight force. And the normal force is always, by definition, the normal force has to be perpendicular to the surface. Now this is a case where the normal force and the weight force are not equal. And how do I know that? Because I break down this weight force into its components right here. So there's this component, and there is, do the x component in blue. So the y component is in green, the x component is in blue. Why am I saying that? We're on a tilt here. Well, remember, we redefined the axis. We said that this is now y and this is now x. Man, I can't write tonight. So we said up and down the incline I'm defining as x, and perpendicular to the incline I'm defining as y. So this is y, this is x. The angle that they give us here is equal to this angle here. Okay? If you want to know, there's a little geometry lesson behind that, but what you need to remember is that this angle is equal to that angle. Okay? That's really important. This is our hypotenuse now. When we do that head tilt, we now see that this is our hypotenuse. Here's our right triangle right there. And so now when I try to find this component, it's going to be the cosine of theta times the weight force. What else did they want us to write on here? The frictional force for number 12. So if there's friction acting on that block, that friction is going to be opposite the direction of motion. So that friction force is always going to be opposite the direction of motion. So if the block is just sliding down the ramp, then the friction force will be up the ramp. If I try to push the box up the ramp, then of course the frictional force would be down the ramp. It's always opposite the direction of the motion. So D was the correct answer for number 12. And number 12 leads right into the number 13. Notice that this diagram is used for question 12 and for question 13. So I saw somebody ask for number 13 on the practice test. Number 13 says, which of the following correctly indicates the magnitudes of the forces acting up and down the incline? So when they say up and down the incline, they want to know these forces acting in the x direction. They want to know the forces acting in the x direction. Well, what forces do we have acting in the x direction? We have the frictional force acting in the x direction, and we have the x component of that weight force. The x component of the weight force is going to be, that's opposite of that angle, so it's going to be mg sine theta. Mg sine theta is the x component of the weight force. These are the two forces that are acting up and down the ramp. It does say it's up and down the incline. It does say that the box is accelerating, right? It does say that the box is accelerating at 2 meters per second squared. So when I do the summation of the forces in the x direction, and that equals ma, I'm going to keep this a over here because the box is accelerating down. If the box was sliding down at a constant velocity, this side would become 0. So what are the summation of the forces in the x direction? Well, we have the weight force in the x direction minus the frictional force equal to the mass times the acceleration. On my key, I did it opposite. I said FF minus the weight force, but we are accelerating down the ramp, and we're going to define that as a positive acceleration going down the ramp because we are speeding up. So the weight force minus the frictional force equals ma. The weight force we've already figured out is mg sine theta, and the frictional force is oh, that's what they want us to find. So we're eventually going to have to find that. I know the mass is 2 kilograms, and I know the acceleration is 2. Let's go ahead and plug this in. Mass is 2, g is 10, sine of, let's see, it's 30 degrees. We'll go ahead and simplify that to 4. So 20 times sine of 30 degrees minus the frictional force equals 4. And 20 times the sine of 30 degrees is 10. So 10 minus the frictional force is equal to 4. So I know that the weight force is 10. And by rearranging this, add FF to the other side and subtract the 4, I get the frictional force is equal to 6 newtons. So the correct answer is D, because this component is down the incline, and we found that right here. That's 10 newtons. So we have 10 newtons down the incline, and the frictional force we found here, and that is going to be directed up the incline. So D is the correct answer. 10 newtons down and 6 newtons up the plane. All right, so that is the answer to number 14. Mia says, someone, and I got you. For 13, why don't we subtract friction? Number 13, we did subtract friction. So the weight force minus the frictional force. They're in opposite directions, so we have to subtract these vectors. Going down the incline, we have 10 newtons of force going down, 6 newtons of force going up. The difference between that is the net force, which is what causes the acceleration. So that is 4 newtons of net force. Divide that by the mass of 2, we get the acceleration of 2. We just kind of had to work backwards on this one, but we did subtract the frictional force from the weight force. All right, what's the next one that you guys wanted to talk about? Number 16? All right, let's look at number 16. Number 16, so if you look at my key, basically I had that picture that in the wrong spot. That picture goes with number 17. So let's look at that real quick. Let's do number 17 first. So this picture where we label point P and point Q, that picture goes with number 17. So it says a ball is thrown and follows a parabolic path like this, as shown above. Air friction is negligible. Point Q is the highest point on the path. Which of the following best indicates the direction of the net force on the ball at point P? So we want to know the direction of the net force of the ball at point P. What you need to know here, guys, is that this is projectile motion. And by definition, projectile motion, the only force acting on it is the force of gravity. So if the only force acting on that object is the force of gravity, well then the net force is directed downwards, and it is mg, and it's going to be mg down there, and it's going to be mg down here. A lot of people want to think that there's some force at the angle at which it's moving up and then back down, but it's not. It's just the weight force all the way down. So D is the correct answer for number 17. All right, so that being said, that picture goes with number 17. What about number 16? And this is why I put it in the wrong spot by accident, because it said the parabola above. Well, the parabola above should have been a graph of a velocity time graph that looked like this. That parabola. I was actually talking about the parabola of a graph, the graph of speed versus speed v as a function of time t for an object. Which of the following graphs best represents the magnitude f of the net force exerted on the object as a function of time? So by looking at this graph, they want to know, what does the force time graph look like? And actually the net force time graph. So if I look at this velocity graph here, what does the slope of a velocity time graph tell us? The slope of a velocity time graph is acceleration. Thank you, Mr. Deese. Is the slope of this velocity time graph constant, or does it change? Well, we ask ourselves, draw some tangent lines, right? No, that acceleration is not constant. Is that acceleration increasing or decreasing? That acceleration is increasing. And guess what? What does our net force do if the acceleration increases? It also increases. And because of Newton's second law, F net equals ma, F net is directly proportional to A. So whatever A does, F does. Now, velocity is increasing exponentially, but the rate at which this acceleration is changing is a constant rate. So the net force graph should actually be a nice linear graph that looks like that. We know it wouldn't be a curved one because the velocity is curved, and if I take the tangents of these, and if I drew an acceleration time graph, that graph would look like that right there. Remember, we go from a curve to a straight line to a horizontal flat line. The FNet versus time and the acceleration time graph should always look the same. Maybe, of course, the scale is going to be different over here, but they should look the same. They should increase by the same rate. All right, so we did 12, 13, 1, 16. Mia's asking for number 14. Let's look at number 14. Number 14. Oh, this is the system of the boxes being pulled by F, okay? So I wrote out a bunch of equations over there, but this is another one of those questions that we can really just use our common sense to do. We have 1 kilogram here, and we have 2 kilograms here, and we have a tension force, of course, in between those boxes, and we have an applied force of F here. Now, like we saw on the last page in our packet, we know that that force, that applied force over here, has to be greater than the tension force in between those two. Why? Because this force has to pull the 2 kilogram and the 1 kilogram. I really could think of it as this force has to pull a 3 kilogram box. Okay, I could think of those two as a system, as one box, and that force has to pull 3 kilograms. Well, how much mass does this force have to pull? It only has to pull 1 kilogram. So if this force has to pull 3 kilograms and this force has to only pull 1 kilogram, well then what is the ratio of the forces? If it has to pull a third of the mass, because 1 divided by the total mass of 3 is 1/3, then the tension force is going to be 1/3. And so it's in terms of F, so the tension force is going to be less than F, and it's actually going to be equal to 1/3 of F, because it has to pull 1/3 of the mass. So I did my summation equations over out on the right hand side, but you don't really have to do all that if you think about it in terms of what fraction of the total mass does this tension force have to support. And it's a third of the total mass. All right, that is number 14. Shannon wants us to look at number 18. That is, oh, that's our graph one. So let's look at number 18. Whoops. Number 18. We have a graph with some data. We have the weight force, which is measured in newtons on the y-axis, and we have the mass, which is measured in kilograms on the x-axis. It says the graph at left shows the relationship between the mass of a number of rubber stoppers and their resulting weight on some far-off planet. The slope of the graph is a representation of what? So what's happening is we have some rubber stoppers here, and the rubber stoppers are increasing in mass. They're increasing in mass. And we know that as mass increases, what does the weight do? It increases. And they say, oh, well, if the mass is this, then the weight is this. And if the mass is this, then the weight is this. And we get this nice graph that is perfectly linear. It's linear. What's the equation of a line? Y equals mx plus b. Now I have to ask myself, do I know an equation that relates weight force to mass? Absolutely I do. I know that weight force is simply the gravitational force, which is equal to mass times the acceleration due to gravity, mg. So weight equals mg. If I compare this to y equals mx plus b, this would be plus 0. There's no plus b in this scenario. I need to rearrange this equation so that I have what plotted on my y? Weight. So I want weight on my y. Good. The equation's already set up with weight on the y. What did I plot on the x? I plotted the mass. Do not confuse this m with this m. This is slope. This is mass. So when I come over here, I want this mass to be on the x. So I'm going to put it, whoops, I was going to write an x. I'm going to put it, oh, I do want to write an x. Hold on. I'm going to put the x here. And if I put the x here and the y equals mx and the b here, then I actually have to flip-flop those two because I plotted m on the x. So weight equals gm plus 0. Now that I've lined that up with my y equals mx plus b, weight's on the y, mass is on the x. What does the slope of this line represent? It represents little baby g. And what is little baby g? The acceleration due to gravity. One of my favorite things to do. Linearization. Mia says, is it possible for you to walk us through FRQ number 2? That is a doozy of an FRQ. So I'm going to ask if there are any other questions before we move on to that. Any other questions about the practice test or the review or the packet before we move on to FRQ number 2? FRQ number 1, section E. Okay, so let's look at FRQ number 1. In FRQ number 1, I do want to point out that we have an inclined plane here, and of course we have this sled going down the inclined plane. Yes, Ethan Keller, you do need to know how to linearize graphs. If I look at this, it has a constant speed or constant velocity, which is equal to 2.4 meters per second. That should be a clue, and I should under that in my problem. If the velocity is constant, then what is the summation of the forces? Summation of the forces is equal to 0. Sum of the forces is equal to 0. So when I draw my free body diagram, I know that I'm going to have, I'll just draw it on a dot here. I'm going to have the weight force, which is going to be straight down. I'm going to have the normal force, which is perpendicular and less than that weight force. The normal force will always be less than the weight force on an inclined plane. Always. Always, always, always. And then I heard a lot of students asking, well, is there friction or is there not friction? If the sum of the forces is 0 and I have a constant velocity down this ramp, then what has to be the sum of the forces in the x direction? The sum of the forces in the x direction has to be 0. And I already know that I have, of course, there's my y component of my weight, and here's my x component of my weight. If I didn't have friction, then the only force in the x direction would be the x component of the weight force. And if I only had one force in one direction, then I have to have a net force. In order for the summation of the forces to equal 0, I have to have a frictional force here, and it has to be equal and opposite to the x component of that weight force. Constant velocity means zero net force, which means I have to have a frictional force there. Okay? On your diagram, do not draw the components. What does that mean? That means don't draw these things right here that I just drew, those red ones right there. You can draw the ones that are in black, which would be the friction force, the normal force, and the weight force. But don't draw the components on a free body diagram if they specifically ask you to draw the free body diagram. Now, over to the side, to do the math on the next page or whatever, you can break it up into those components and that right triangle. But on a free body diagram, never draw the components. So I know the summation of the forces is going to be the x component of the weight force minus the frictional component, which is equal to 0. Therefore, the weight force is equal to the frictional force. And then we go through a series of steps to figure out what the frictional force is, what the speed is, or not the speed, but the time it takes for it to go down the ramp. We figure out mu. Remember, we're going to be chanting the equation for frictional force is mu Fn, mu Fn, mu Fn. Don't forget, frictional force has its own equation. And then we get down to part E. Part E says the sled reaches the bottom of the slope, so that would be here, and continues on the horizontal ground. So it's going to continue moving straight on the ground due to its inertia. Assume the same coefficient of friction. In terms of velocity and acceleration, describe the motion of the sled as it travels on the horizontal ground. So what happens is that the minute it hits the ground, I still have that frictional force acting parallel to the plane and opposite the direction of motion, but now the weight force is totally down and the normal force is totally up, and now those are equal again. So the only force acting on the box now, or the sled now, is this backwards frictional force. And if that is the only force acting on my box, then that means I'm going to have an acceleration. And since the frictional force is directed to the left, and that's my net force, then the acceleration has to be directed to the left, because acceleration and net force are always directed in the same direction. However, the motion was to the right. So what does that mean my acceleration is going to be? It's going to be negative. The acceleration is going to be negative because it is opposite the direction of motion. Anytime the acceleration is opposite the direction of motion, it is going to be a negative acceleration. So how would I describe it? How would I describe the velocity and acceleration? I would say the velocity of the sled after it hits this point is going to decrease. It's going to slow down. We know that. The acceleration will be constant. So that acceleration is just the rate at which it slows down, and the rate of that slowing down will be constant because we're on the same surface the whole time. So what they want us to do in E2 is to sketch the velocity time graph. So here's velocity, here's time. And they want us to start it, they want us to include the sled's travel down the slope and across the horizontal ground. So they want me to figure out the velocity time graph as the sled slides down the ramp and goes on the horizontal ground. So what type of motion did it have on the ramp? Constant velocity. What does a velocity time graph look like for constant velocity? Constant, not changing, right? Constant velocity. And then when it hits the ground, well, then we said that the velocity starts to decrease because the acceleration is negative. So if the velocity begins to decrease, what's going to happen here? That graph's going to go boop, all the way down here. Remember, this is 0. The velocity is going to decrease until it stops, till that sled stops and reaches a velocity of 0. What is the slope of the velocity time graph? It is acceleration. And what type of slope do I have here? A negative or positive one? I have a negative slope. So everything that I've described and drawn here is consistent. So that is part E for FRQ number 1. Yes, Samantha, you're correct. Sophia says, what would the acceleration time graph look like for that? Oh, acceleration time. So the acceleration time graph is just I'm gonna look at the slope of the velocity time graph. The slope for the first section going down here was 0. There was no acceleration. Remember, acceleration was 0. So for the first part, the acceleration was 0. And then for this part, so slope equals 0 here. And then here, the slope is negative. So my acceleration would be negative, and it would dip down like that. So I'd have a 0 acceleration and then a negative acceleration. That's what my acceleration time graph would look like. All right, number 18 and 19. Number 18 and 19. 18 and 19. 18 we already worked. Number 19. All right, number 19. Three forces act on an object. If the object is moving to the right in translational equilibrium, which of the following must be true? Translational equilibrium. First of all, translational just means kind of in a linear motion. When we get to next semester, we'll have rotational motion. So it's either, motion is either translational or rotational. Rotational means it's going to be moving in a circle. It's going to be rotating about a center axis. Translational motion means if I start here, well then I'll end up some, direction away from that in a straight line. If I start, rotational motion means that if I start here, I'm going to be rotating in a circle. Translational is linear, rotational is that rotating motion. So if I'm in translational equilibrium, and equilibrium just means that everything's balanced, right? If I'm moving to the right, I'm horrible at these drawings. If I'm moving to the right, so this guy is moving this way, but I'm in translational equilibrium, what that means is that the net force acting on it in the x direction is going to be 0. Okay? They tell me that there's 3 forces acting on the object. So if there's 3 forces acting on the object, then the vector sum of all of those forces must be equal to 0. This translational equilibrium basically was just saying that it's moving at a constant velocity. And if I'm moving at a constant velocity, then the sum of all the forces, some of the forces in the x have to be equal to 0, and the sum of the forces in the y have to be equal to 0. So all the forces, the vector sum of all of those forces have to be equal to 0. And of course, D, the object must be moving at a constant speed because it's in translational equilibrium. All right. You guys want to take a look at FRQ number 2? It didn't specify, Matt, what the forces are. It could have been maybe I have another downward force here, or maybe I have an upward force here. It didn't specify. It just said 3 forces. Okay? Maybe it was a frictional force and then a weight force and a normal force. Or maybe it was an applied force and a weight force and a normal force. It didn't specify. I just know that the sum of all of those must be equal to 0. Well, yeah, one of them would definitely be the weight force, especially if we're near a large planet, right? If we're in a gravitational field, we're going to have a gravitational force. That's way more than 3. I gave you lots of options to choose from. All right, let's look at FRQ number 2. FRQ number 2 forces you to do something that you guys don't like to do, which is work in terms of just variables. There's no numbers given in this problem. They want you to express all of your answers in terms of h, m, and g. And they have defined for you what h, m, and g are. Determine the acceleration of block B as it descends. What we have here is a modified Atwoods. Number 2, FRQ number 2, nothing this complicated, no. You will definitely have to express things in terms of variables, but not a whole free response question like this right here. So we'll just do a little bit of it here. We have a modified Atwoods, so we have a surface, and then we have a hanging mass. So we have a surface mass and a hanging mass, and those masses are both m. How convenient. Those masses are both m. They tell us the distance here is 3h, and they tell us this distance, I think from here to here, is 2h. So they're giving us a ratio of those distances basically, and they're telling us that from here to here is h. The first thing they want us to do is to determine the acceleration on the block B as it descends. So I need to write a summation. Well, first I need to draw a free body diagram, and I want to think of this as a system, because the sum of the forces on a system is still equal to the mass of that system times the acceleration of that system. So I'm going to say the total mass of the system is equal to the acceleration of the system. So this is system, system, system. And I defined both of those masses as my system. So the sum of forces on both of those masses equals the sum of their masses times the acceleration of those masses. By the way, this block and this block will have the same acceleration because they are connected. That just kind of makes logical sense, right? That they will both accelerate at the same rate because they are connected as a system. All right, acceleration of the block. I can rearrange this and say acceleration is equal to the sum of the forces divided by the total mass. The acceleration is always going to be a ratio of the sum of the forces to the mass. So now I just have to ask myself, what's the summation of the forces? Well, the trick that we used in class is that we pulled this guy up here so that we could get all of those forces in the same plane. So I have a weight force of mg here. This one's on a surface, so this mg is that way. I have a tension force here and a tension force here. And yeah, I have a normal force because this is a surface. And we did not have friction in this one, correct? Smooth tabletop, so no friction. So no friction force there. Well, the motion is going to be to the right, so I need to sum up those forces that are in this plane right here, in the x-plane. The normal force and weight force are going to be equal to each other. They cancel each other out, so the summation of the y forces is 0. So what that means is that Fn minus mg equals 0. So we know that Fn is equal to mg. Over here, these two forces cancel each other out because they're equal and opposite. Those tension forces are equal and opposite. So the sum of the forces is just mg. And then the sum of the masses is m1 plus m1, or sorry, m2. But in this case, they're both the same m. So really it's just mg over 2m. And I can cancel out can cancel out those m's, so the acceleration is just g over 2. The acceleration is half of g, which would be about 5 meters per second squared. They didn't ask us for the value, but it would be g divided by 2. This would be the final answer for that one. It says block B strikes the floor. It does not bounce. Determine the time at which block B strikes the floor. This is going back to kinematics. And if I know height, I know time. If I know height, I know time. And we use the equation delta x equals 1/2 at squared plus v naught t. Because this object is accelerating, I want to know the height. I want to find the time, but I'm going to use the height to figure that out. So the height at which it falls from is going to be this distance here, which they've defined as h. So I'm going to say h is equal to 1/2 a, but we've already said a is equal to g over 2, times the time squared, plus the initial velocity. But the initial velocity is going to be 0, so that whole thing there goes to 0. So now I just have to simplify this expression. And we need to solve for t. So g over 2 times 1/2 becomes g over 4 times t squared. So I need to isolate t. To isolate t, I'm going to multiply by 4 and divide by g. So I'm going to have 4h over g equals t squared. I need to take the square root of both sides to solve for t. So the square root of 4h over g is equal to t. That is the time that it took to hit the ground. Part C says describe the motion of block A from time t equals 0 to the time when block B strikes the floor. So what's going on with this block here, A, in the time that it takes for this block to hit the floor? Well, we know that block B is going to pull it down with an acceleration of g over 2. So block A is going to accelerate to the right at g over 2, or 5 meters per second squared. So block A will have the same acceleration as block B. Yes, Samantha, your forces packet needs to be turned in tomorrow. Then it says describe the motion of block A from the time block B strikes the floor to the time block A leaves the table. So what happens is once block B is on the floor, block A has not reached, block A has not flown off the table yet. So block A would be accelerating, and if I were to draw an acceleration time graph for it, it would have a positive acceleration for the time that block B is in the air. But once block B hits the ground, there's no longer a net force pulling on block A, so that acceleration would actually go to 0. So this is before block B hits the ground, and this is after block B hits ground. So this would be the acceleration time graph for block A. That would kind of be the title of this graph, is that it's the acceleration time graph for block A. And this portion of the graph would be after block B hits the ground. Determine the distance between the landing points of the two blocks. This is more kinematics, and you have to combine a couple of equations. But if you want to figure out, if you want to see how to do that, just look at the key. It's there. It's a little more in depth and a review of what we did in our last unit. We are at 9:10. We've been in this for an hour. I'm going to give you guys a chance to ask some last minute questions. While you're thinking of some questions, I'm going to think of some important things to remember. Important things to remember. Inclined planes. The weight force will always be down, and you're going to break that weight force into its components. And this theta is equal to this theta, always. So what that means is our right triangle is here. If this is our weight force, then the y component of the weight force is going to be equal to W times cosine of theta, and the x component of the weight force is going to be equal to W times sine of theta. This is opposite of what the y usually is. In all our other problems, the y component has been sine of theta and x component cosine of theta, but this you need to remember. Anything you should definitely study. The elevator problem. So I spent some time on that elevator problem earlier in the review for a reason. You will definitely need to understand the elevator problem. You will definitely need to understand this right here, what I'm saying there. And what else? What other hint can I give you? Inclined planes and elevators. Understand, make sure you understand a problem like number 15 on the test, where you have the force at an angle, like that right there. And in this case, the y component, if this was F, then the y component of F would be equal to F sine theta. So in this case, the y component is sine, but in the inclined plane case, the y component is cosine. And this is really the only time that we see the y component being cosine of theta. So that's kind of an important thing to remember. Will you be answering questions before school? Taylor, yes, I will be there tomorrow before school. Sometimes it's a madhouse in there before school, so if you have questions, you've just got to like plow your way through, and you know, squeaky wheel gets the oil. So you need to make sure that you get my attention. I don't know, maybe some tacos, or no, I'm just kidding. Make sure you get my attention and you get your questions answered, because usually there's going to be a lot of people in there before the test. I'm going to tell you that you do need to study. You need to practice. You need to study. You need to practice. There are questions at the end of the chapter in your book. The misconception questions are great questions, and the problems, none of the really detailed mathy crazy problems, because this test is more conceptual, but you will have to do some math, and I think the answers to the problems, the odds are in the back of the book. Okay, so if you're wanting some inclined plane problems to work, look at the end of the chapter under the problems. There's 3 sections. There's a section called questions, which are always great. There's a section called misconception questions. These are usually multiple choice questions, great to look at. And then there's problems. The answers to the problems are your more traditional math problems, summation equations, those type of things. The answers to the odds of those are in the back of the book if you're looking for extra work. Of course, do the packet, finish up the packet, and I don't have any extra problems for you guys to work. I might be able to scrounge up a few things if you guys are looking for more work, okay? Mia says, is it possible to do some of these webinars before the final review, like a halfway mark review? Oh, I see what you're saying. So instead of just the night before, like a halfway mark. We might be able to do that. Let's keep that option open, Maya, okay? Let's keep it open. Mia says, so where exactly are these misconception questions if you haven't mentioned them already? They're at the end of the chapter in the book. So at the end of every chapter, there are multiple choice questions, and they're titled misconception questions, and they're great because they expose the misconceptions, the common misconceptions that we have about whatever chapter it is we're looking at. And I do have the answers to all those, so with explanations. So I'll just share that with you guys on Google Classroom. I can just share the answers to all the questions, misconception questions, and problems. It'll be more than what you need, but that way you can do any amount of questions at the end of the chapter that you want. I'll share those answers with you. Okay? Just make sure you study, guys. Make sure you practice, and if you have questions, let me know. Thank you for participating, and good luck studying. Have a great night, and I will see you guys in class tomorrow.